So what will probably be end up being the last in the live integration series for a little while. I'm going to do a little bit more of it. I got school starting up, so yeah, I'll probably just do one more of these and then try and do them every now and again, since it does seem like some people have enjoyed them. I'm going to do this one a tiny bit differently. What I'm going to do if I change this is I'm going to select the numbers first. I was going to say I was going to select three of them, but since the first one is 25, I might select four. Um, anyway, I'm going to select all the numbers first, and that way we can just give me such low numbers. Hopefully, though, if we take a few of them, we get a nice one. Um, why are they going in order as well? Do we trust Google's randomness? Is that something that we trust? Anyway, 349. So let's bring up all four of these, and then we can just look at them. And I think that would be a nice way of doing it, because that way we can select which one we want to do first. We can have a think about all of them at the same time for a second, and it also helps you to navigate the video if there's one that you don't want to see. For example, integral number 25. Maybe you can't be bothered to do, just like I almost certainly can't be bothered to do it, but we'll do it anyway. So it was the integral of 1 plus 2 cos of x. I think that was all cubed, if I'm not mistaken. And then, oh, which PowerPoint is, what are you doing, PowerPoint? Cube it. I mean, that was my bad. What is going on here? So we're just going to do this because apparently PowerPoint has broken some amazing stuff. I hope that doesn't happen throughout the video, but hopefully it was just that text box acting weird. I think that was the integral. Okay, so before we do that, we're going to find integral 144, which is going to be, so this is it's going to be a bit of a slower start to the video. X log of 2x cubed is the next one, but hopefully it'll pay off because you'll see all of them in one go. So x log of 2x cubed is the next one, dx. And the one after that was 628. Now that one's probably going to be quite hard because it's quite late in the series and it looks quite interesting. It's something that I absolutely can't remember, but it was at least a fraction. So I'll input the fraction first. As we'll stick the dx at the end as well while I'm here. And what was going on here? Xe to the power, I think 2x squared. Was it, or was it? Yeah, x, okay. And then root. What on earth is this? Well, this one, we know which one is going to be the time-consuming one in this video. 2e, and then the same thing, right? 2x cubed, or squared. Let me check. Okay, right, and then the last one is 349. 349, which is 5 to the power 2x. So we've got more exponentials going on, which is interesting. So we've got 5. Oh, what's this going on? PowerPoint, don't do this to me. 5 to the power 2x. And then I think it was just something plus 5 to the power 2x. No, 5, well, technically, yes. 5 to the 2x plus 3. Okay, so these, like I said, let's display them all. These are the four integrals we're going to do. I might just attempt, just because it's really playing on my mind. I'm going to try and type this again. If I do it like this, PowerPoint's going to be much happier about it. What are you doing? I mean, what are you doing? Why is this not something like that? Right. And then 1 plus cot 2, 1 plus 2. Sorry, this is the price you pay during. Yeah, okay. At least it's worked now. Dx. Cool. So we've actually got this to work. Now, this one immediately strikes me as being possibly, well, it's only integral 25, right? Um, the derivative of this bracket here is just sine of x. It's not. It's minus 2 sine of x. So if I just shove in a minus a half, and then 1 plus 2 cos of x to the power 4, and then you'd also have to consider the 4 that comes down. So I think if you put an 8th there, 4 times an 8th is a half, times this 2 is 1. Bring this down to a 3. The derivative of 2 cos is, we've already used the 2, is minus sine. And I think that's the answer to 25. So that one was the easy one. I did 4. I was planning to do 3, but I did 4 just because I knew that one would be relatively easy. Let's do 144 next. I think I'm going to leave, as you can probably tell, that one to last. I think I at least have a good idea about this one. I'm not so sure about this one right away, but we'll plow through. So let's get rid of this. We've done 25. We can also just get rid of all this, because who needs it? Okay, so x log of this thing here is kind of an interesting looking integral for sure. Immediately, parts seems to be a thing that we could try. Obviously, I can integrate the x to x squared over 2 and then leave this object alone, and then I could consider what happens. Of course, parts sprung to mind because the derivative of log is just like it's just of a polynomial. It's just going to create more polynomial stuff. It's just 2x cubed, and then the derivative of that is 6x squared. So of course this all comes together to make 3, I guess. Nope, what am I doing? To make 3 over 2, I think. And then is this just x left over? So this I think has been done. So it's going to be this into 3 over 4 x squared. Something like that. So I think that one is also done now. So let's get out the third one of the 4, which is, I'm going to say this one, because we're going to leave that last one to last. Now this immediately hits me, because this is a super easy integral if that was an e and that was an e. Because if that were the case, the top of this is essentially just the derivative of the bottom. So it's of the form k, I guess, f dashed of x over f of x, which means its integral is just log of f of x, except it's not, right, because of that constant that we mentioned. The derivative of that is actually 2e to the 2x. So if I just shove a half in here, this is fine. So this is very similar, except that the derivative of 5 to the power 2x plus 3 is equal to 2 lots of 5 to the 2x. That works the same. But then you also times by log 5, I believe. Because essentially the derivative of e to the power 2x is essentially 2e to the power 2x times log of e, but the e goes away. So I think that's fine, which means if I were to integrate this, what I want on the top to make this derivative match is I want a log 5 here. Well, I want a 2 log 5 here, right? Now this derivative matches. So, of course, to compensate for that, I can put a 2 log 5 here. And so now the integral is 1 over 2 log 5 of what were just talking about, 5 to the power 2x plus 3. So I think that works. So I think that's all good to go. Okay, so the last one then that we'll do is 6 to 8, which is this one here. Hopefully there have been no complete blunders so far. Okay. Wow. So what is going on here? This is pretty crazy. Now, I think that what's interesting to me is that the derivative, this is similar to what we just saw, I guess. The derivative of e to the power 2x all squared. Is this what I'm looking at? That's kind of what I'm looking at. Now, what's the derivative of that? So it's e to the power f of x. So the f of x breaks brought down and derives. So that makes 4x. So this is 8x, because you times by this 2 as well. And then you just leave the e stuff alone. So it's still e to the 2x. And now what's interesting about that is that that is this, just with a constant. So if I wrote this as not this here, I copy pasted and now I'm going to have to copy paste something else, so I'm going to type it out. But if I wrote it like this, 2x squared, like, come on, like this, sorry, but then to the power minus a half. I think this is imminently doable because this is an integral of the form f dashed times f, right? With a constant. I can't bother to type it. But this is the derivative, as I've just pointed out, of this thing here. to a constant. So I think all I have to do is raise this up by 1, delete all this because it's good. It should be there. And then just account for this. So the derivative of that was 8. And then you'd also times by a half to make 4. So I think just a quarter. I think that's all I have to do. Um, maybe I've been mistaken there, but I don't know. I think that's gone pretty well. I think that's all I had to do. Cool. I mean, I was scared of it because it looked weird. I thought I'd have to use some kind of horrible substitution, but I think it was actually quite easy. That hasn't lasted very long, has it? 10 minutes 41. Bonus integral time. Let's do a bonus integral. Exciting stuff. 565, just for our bonus. Okay, well, this one looks fun. 6 over. So yeah, bonus integral time. What a lad. 1 over. No, was it 6 over? Something? My memory is so poor. 1 over cos squared. Cos x is cos x all squared, I should have said. Something like this. Cool. Is that all good to go? Looks like it. Good. Okay, so what is happening here? So, what number was this? Just so I know how hard. 565. Okay, so it's going to be reasonably difficult, probably. Not that yeah, that probably wasn't the best tactic to use, but yeah. Okay, so we could expand out. Does that help? Something I did in the last video was use double and half angle formulas, and I'm wondering whether that helps. So, for example, I'm going to always start in the place where I always start. This is cos squared minus sine squared. Now, I'm not particularly interested in that. What I'm more interested in is that makes this, that's 1 minus cos, that's going to be 2 here, and then minus 1. And then I'm also interested in what happens if you halve this angle to halve this one. And then if I add 1 to that, to both sides, that 1 goes away, and we end up with this. So that was quite successful. So something very similar to what we did in the previous video. Now that squares, of course, to make 4. Ooh, don't want that square anymore. 4 cos, oh, need a cos, to the power 4 x over 2. Well, that's particularly interesting because we actually did this integral a couple of videos ago, right? It's x to the power 4. We did this one, I think. So I think we just have to do it again. Yeah, we did this. Now, this is the point where I have to admit that someone wrote in the comments, nice way of doing sec to the 4. And I can't remember what they wrote because I have to admit, I think I skim read it um, to some degree. They wrote something nice about um, it was just a shortcut. I think I didn't read it properly because it was just a bit of a shortcut. I remember I did it like this, right? I said this was, I mean, the integral of that is 2 tan x over 2 because this is a mistake I made in the last video, actually. This integrates, of course. I think I put a half here on something similar. And then this is going to keep being sec squared. Of course, just leave that one alone. And then we're going to take away the integral of the 3 over 2 is actually still applies, so that's going to be 3 over 4. And then we're going to take away the integral of, well, we still need a 3 over 2 here. Still integrate this one, which is still going to be a half tan of x over 2. And then was it the derivative of this that someone pointed out was easier to do? I think I derived it by doing some mess of sines and causes. But if you say sec squared is 1 plus tan squared, this derivative is easier to do because it's literally just it's tan x over 2 all squared. So the 2 comes down, the half comes out, which cancels. So you're just left with a half. Sorry, you're just left with tan x over 2 times the derivative of tan, which is sec squared x over 2. So I think sec squared must differentiate, because sec squared is this, must differentiate to with the x over 2, tan x over 2 times, oh no, wait, I've got that, yeah, times sec squared. So, well, the tan of x over 2 makes that a tan squared. And then I'm also going to have a sec squared here, because that's what the tan derives to from this derivative here. So, sorry, this should be an x over 2. I'm going to have to make the font a bit smaller so it fits. Not that small. Okay, so we end up with all of this. And now, was it pointed out, like, so this is, and now am I doing the same thing I did last time, which is sec squared is obviously over cos squared. Tan squared is sine squared over cos squared, which makes this sine squared over cos to the 4, which makes this, I'll put the half there, by the way, which makes this 1 minus cos squared over cos to the 4, which makes it 1 over cos to the 4 minus cos squared over cos to the 4, which is sec squared. So this is the integral of sec to the 4 x over 2 minus the integral of sec squared. I think this is what I did last time. Maybe I've missed the trick again. Maybe that wasn't what they wanted me to do. I honestly can't remember. But this is now doable, because this is just this, right? Yeah, this is just this. So if I call this I actually don't think I can bother typing the rest of this up. But we did the same thing. It's the same thing we did before. This is the integral we're looking at. We call it I. 3 over 2I equals all of this, where this is also I. This is minus 3/4 I, and this is plus, I guess, 3/4 tan x over 2. Also, you have to times that by 2, so 3/2 tan x over 2 when you integrate that bit. And then, of course, you can add I to, or 3/4 I to both sides, and then divide by the remainder, and you end up with some integral, I think, that is done. So I think that's how we go ahead and do that. Yeah, good. Anyway, that was the bonus integral done. Feel free to point out things that I've got wrong. But yeah, I think that was fairly successful on the whole. Thanks for watching, and I'll see you next time with one of these, maybe a little bit further into the future.